So now we're going to talk about a little bit more about this choice of the analog format of the digital information that's going to be transmitted over the air. So we saw so far two possibilities, PAM and PCM. Those are both what we call baseband modulation. There's two things. We can have what we call baseband, or we could have passband. Two types of communications. The difference between baseband and passband is that the passband uses a carrier frequency. That means instead of having the information be centered at DC, which we call baseband, instead of that will be like a cellular telephone where we take the voice, which is typically, a baseband, and we take that voice and we put it up on a higher frequency, like 900 megahertz or something for the actual transmission by RF means. So you could either have baseband, no carrier, or you can have passband with a carrier. Okay, so we'll talk about that later, and actually we'll talk about that mostly in the abstract. But I just want to mention that now when we're talking about PAM and PCM, these are actually examples of the baseband variety. And so what we're going to be talking now, you'll see, is discussed as baseband modulation. And in particular, I'm going to just talk very briefly about some options we have for the waveforms. So we saw something very simple in the case of PCM and PAM, these rectangular shapes. Later on we'll talk about things that are not necessarily rectangular, but even if we stay in the realm of the rectangular, there are already many options we can use on how we would transmit the information. So I'd like to talk to you now a little bit about what we call line codes, which are a variety of ways we can format the analog waveform which is going to be transmitted. So the baseband modulation waveforms are covered in our Scholar textbook in section 2.8. So we've seen PCM versus PAM. In the PCM, or the pulse-coded modulation, we have binary transmission, and we know that it takes faster transitions in time, which means wider bandwidth solution. Pulse amplitude modulation, the same, we have multi-level transmission, so it's not just two levels, there's multiple levels. And this can be slower in the time domain, which means it could be narrower bandwidth. So that's what we've seen so far. But as I said, we can generalize things a lot more. So one of the first simple distinctions that I'm going to be discussing is what we call RZ versus NRZ. And these two possibilities are an example of what we call line codes. And there are many varieties of line codes, and I'll show you some of them, and there's a lot more discussed in the textbook. But the two fundamental examples of a line code fall in this RZ and NRZ, so we'll start with that. Now the RZ, what does that stand for? It stands for return to zero. Return to zero means that we're going to have a quiet time between subsequent bits or symbols, really. All my examples are going to be bits, but you could apply this equally well to symbols. So I could have this quiet time, and I'm going to show you some graphics that show you what I mean by that. Or NRZ means non-return to zero, so none of this quiet time nonsense. We just go bit to bit to bit, or symbol to symbol to symbol. So let's see what this looks like. Let's start with binary data. And again, I'm going to suppose these are baseband transmission, for instance, of PCM, because PCM is, of course, a binary example. So up here on top, I have my logical information that's going to be sent, logical 1, logical 0. And in this time, that capital T represents the bit duration. And so I have a couple of ways that I could code this, a line code. And one possibility would be what I call NRZ, non-return to zero. Now here I'm having plus V volts and minus V volts. So this would be what we call antipodal signaling, which is one variety. I said this was a logic 1 and a logic 0, and now I just say a logic 1, I'm going to call that a plus V volts, and a logic 0, I'm going to transmit a minus V volt. Okay, and here, it does not return to the 0 value. It either goes to whatever the level is for logic 1, to the level for logic 0, non-return to 0. Now, suppose I do something else. Suppose that I don't take all of the time available to me for the bit to actually have an active voltage. Suppose that instead I take some percentage. there's some duty cycle where I only use 1/3 of the time to actually send a voltage. For instance, here, in this example, it's the middle third of a time of a bit where I actually send a level. And the level I send is maybe a plus V volts for a logic 1, and when it's a logic 0, I just don't send anything. Okay, so there's a couple different ideas here, but clearly there's this return to 0 where not the whole time of a bit is used for the voltage that's being transmitted. So that gets an example of RZ and NRZ. And of course, this is like a third, but it could have been any percentage. You know, that's a parameter I can use. So this is one idea of, even if I'm using PCM, there's different ways I can use it. I can use it this way, antipodal, use the whole time, not antipodal, and use just a small percentage of the time. That's one possibility. But there are a lot more. So here's the summary, like NRZ with the bilevel. And I could have RZ, and I showed you just now an RZ which was a unipolar, so it was either logic 0 or when there was the actual 0. And when there was a logic 1, you know, I went to plus V volts, and then for part of the time then I returned to 0. But when there was a logic 0, I said nothing. So that's why we call it unipolar. Or it could be bipolar, so it looks kind of like the NRZ. Now I'm going from plus V to minus V, except there's always a time in the middle where I return to 0. And this is the very classic return to 0 format, where it's like a 50% duty cycle. So half of the time you're sending the voltage, the other half of the time you're sending nothing. There are all kinds of variations. One of the variations, let's just look at the NRZ case. And this is another way of coding the NRZ data. And when you're looking at that and you don't quite see what is this correspondence going on here, because here I have a plus V for a 1, but I also have a plus V for a 0. And what does this mean? So to give you an idea of how you come up with this one, it's actually based on when I get a 0, don't change the voltage. So here I was at a 1 and I was at a plus V. I came to a 0. I didn't change the voltage. I kept it at a steady value. Then the next one was a 1. A 1, I toggle the value. So if before it was plus V, I toggle it to minus V. The next one is a logic 1, and so I toggle it again. Next one is 0, stays the same. So you get the idea. This is another kind of way of defining the transitions. And I could also go where it was just the opposite definition. So this would be an example of a line code. It tells you, basically I'm still using rectangular pulses. It's the duration and also the correspondence between the logical 1 zeros, and it could be each one separately, or it could be based on the sequence of 1s and 0s. You can look at some characteristics that might be different depending on which one of these line codes that we use for our transmission. For instance, we notice here that there's a long period of time when there's actually no voltage being transmitted. No energy is going to be received during this time, and maybe that could have a negative impact on clock recovery or other aspects of the receiver. So this is a characteristic of the RZ signal that makes it interesting or not interesting. Here, for instance, there are fewer transitions maybe than in this direct value. So if we counted the number of transitions, maybe there were fewer of them with this. These are the kinds of characteristics that are the reason that there are such a variety, is to be able to look for different characteristics that are desirable in different kinds of circuits, different kinds of communication systems. So there are a lot of others. I don't want to go through all of them. They're listed in the book, but there's return to 0, alternate mark. For instance, this biphase 1 is an example because there's a whole lot of transitions, and sometimes having a lot of transitions are important for clock recovery. That it gives a lot of, it's a lot easier to reduce jitter and get good timing recovery. If we have a lot of transitions. So different kinds of line codes, each one with their own kind of characteristic. One way that we can look at the characteristics of these line codes is ask ourselves, well, what is the power spectral density of this choice on how I code my system? And so we have here we can look at the frequency content. It can be very different. For instance, here in this solid line, in this dicode NRZ, you can see there's very little content at 0 at DC. And so maybe, you know, whether you're going to use DC coupling, AC coupling, you know, different kinds of features may be interesting. And that's another reason why these different line codes exist. For instance, if you have a DC component and you want to support AC coupling, you want the DC equal to 0, then the dicode NRZ that I just showed you could be interesting. Clock recovery, more frequent transitions. So this idea of forcing a return to 0 sometimes can give you more transitions, especially if you have bipolar. Guaranteed transitions, no matter what the sequence, even if you get a long sequence of zeros together, you know, you always have guaranteed transitions. There's some for that. Bandwidth efficiency, so RZ is very bad for bandwidth efficiency, NRZ is very good. So it depends on which one is how important bandwidth efficiency is for you. Because of course, NRZ has fewer, the duration of the bit is longer. Longer time means less bandwidth. Easier detection, there's differential coding that could make for an easier circuit at your receiver. Noise reduction, all these things can vary depending on, for instance, power spectral density or other characteristics. So that's why we have a variety of line codes in communications. And I won't be talking about that much in the rest of the class. I just bring it up to you to make sure that when you read later on about communication standards, you'll be able to understand what they're talking about when they reference certain line codes. Okay, now I'm coming down to what I think is the heart of this class. I believe that if you really want to understand communication systems, there's 3 things that you have to understand. And when we're going to be comparing a system, you know, like how good is my system? How good? How good? Well, there's going to be 3 ways that we're going to say it's good or bad. First thing is power efficiency. Power efficiency means how much power do I have to transmit in order to get reliable communications. For instance, if I have a cell phone with a very small battery that I would like to last for a long time, then I would like to perhaps use a very power efficient system. And so, of course, if I dial the power down, maybe I'll make a lot of errors. But I want to compare them. Suppose I have the exact same power on 2 communication systems, but one of them has a lot fewer errors. Well, that's what I mean by power efficiency. For the same power, how many errors do I get? And so for that, we often use something called the bit error rate, or the BER, versus SNR, which is the signal to noise ratio. So of course, if I have more powerful signal, then the signal is a lot stronger than the noise, so the SNR is high. And so I want to know, for a given SNR, what's my bit error rate? And so that will be one of the criteria. Sometimes I call it the BER versus SNR, or sometimes I call it power efficiency. But that's certainly, how good is it? That's one way of determining how good it is. The other thing is spectral efficiency. Let's go back to the cell phone. Cell phones are the most demanding of communication systems. They're really demanding on all the criteria. But in spectral efficiency, if I'm TELUS or Rogers and I want to have a larger frequency coverage, I have to pay billions of dollars for that. I pay billions of dollars to get the right from the government to exploit a certain band of frequency. So once I've paid so expensive a price for a band of frequency, I want to put as many clients, as many cell phone users as I can in that given allocation I have of frequency. So that means I want to be very spectrally efficient. For a given amount of bandwidth, for a given frequency bandwidth, how many bits of information can I shove through? How many clients can I support? So we often have a symbol of eta, which represents the transmission rate, how many bits per second, how fast the information I can send in a given bandwidth. So this is what I call spectral efficiency. And the third is, shorthand is dollars. It's how complex is it? Because of course, it's not surprising that if I throw a lot of money at the problem, that I can find some tricks that will allow me to give it better power efficiency or better spectral efficiency. So, but I can't have all these really good power efficiency, real good spectral efficiency, and it doesn't cost much. So there's always a trade-off. So these are the three criteria. Every time that you think about, is this a good communication system, you have to answer this question. And how much it costs depends, right? If I'm going to buy an iPhone that costs $1,000, the radio is allowed to cost some money because, you know, it's a small part of it. If it's a wireless key for your car, well, that shouldn't cost $1,000. That should cost like $2. And so I want something that's like really cheap, and maybe I'm willing to compromise on the other things. So every communication system is different. Everyone will look for a different compromise, but all systems will be based on how do I do with these three. So we've started to see in this simple introduction some of these issues: bandwidth, spectral efficiency, PCM versus PAM. We talk indirectly about cost, because all this about is easy to recover the clock, it's hard, I can use it with this kind of hardware, that kinds of hardware. Well, that's the kind of thing that's going to be influencing that. It's not the kind of thing we're going to be talking in our class. Like I said, I mentioned line codes for now, it's the first time. But when we start talking about cost and complexity in this class, it's going to be about the level of digital signal processing that was required, because that means how large a VLSI circuit am I going to need to add to my communication system, and other things. But anyway, I don't want to get too far ahead of myself, but these three criteria, definitely, rest of the class, we're always going to be talking about them.